In the previous session, the method of slices was discussed to estimate the factor of safety of a finite slope. So in this session, it will be discussed about the friction circle method and Taylor's method. In the friction circle method, to estimate the factor of safety, we have to draw the slope to some scale. So ABD is the slope. Then we have to locate the center of slip circle. And by taking the center O and radius R, we can draw the slip surface AD. So for this slip surface, which is like arc of a circle, we have to draw the chord AD. AD is the chord length and this AD is the arc length. Then we have to find the arc length and chord length using the equations pi r delta by 180 and 2r sine delta by 2. Delta is the included angle. So after that, we have to draw a friction circle at center O with radius kr sine phi. If k value is not given, we should take it as 1. R is the radius and phi is the angle of shearing resistance. Then we have to find a distance r into arc length by chord length. We have to find a distance A which is equal to r into arc length by chord length. With this distance from point O, we have to draw a line parallel to the chord. So this line represents the total cohesive force which is located at a distance A from the center of slip circle. So after preparing this line, which is representing the total cohesive force and is equal to the mobilized cohesion multiplied by chord length, we have to estimate the mobilized cohesion. So for that, first we have to draw the line representing the weight of sliding soil mass with respect to point O or point A. Then this line has to be extended vertically downwards. Then we have to draw this weight value to some scale representing the weight of sliding soil mass. Then we have to get the intersection point of this total weight and total cohesive force, and from that intersection point we have to draw a tangent to this friction circle. So this line represents the resultant reaction, resultant of W and C. Then from this line, whatever is drawn representing the weight to some scale, from the top of this line we have to draw a line parallel to C, and from the bottom of this line we have to draw a line parallel to R, so that one triangle is constructed which is called as force triangle. So after getting this force triangle, then we have to measure the distance for this line representing C. So for this line we have to find the distance. Then this weight value is plotted to some scale. Okay, that will become the load scale. Then this distance has to be multiplied with that load scale. So that we'll be getting the total cohesive force. So that total cohesive force, which is the product of mobilized cohesion and chord length, we can get the mobilized cohesion, where mobilized cohesion equal to total cohesive force which is obtained from this force triangle divided by chord length. So knowing the mobilized cohesion, we can calculate the factor of safety with respect to cohesion, which is equal to ultimate cohesion divided by mobilized cohesion. So using this method, we can find the factor of safety with respect to cohesion only. So there are some examples here. An embankment has a slope of 2 horizontal to 1 vertical with a height of 10 meter. It is made of a soil having cohesion of 30 kPa, an angle of shearing resistance of 5 degrees and a unit weight of 20 kN per meter cube. The radius and chord lengths of the slip circle are 20 meter and 27 meter respectively. Weight of sliding soil mass is given as 2448 kilonewton, which is acting at a distance of 13.5 meter from the toe. Use the friction circle method to find the factor of safety with respect to cohesion. So here chord length is given, arc length is given. So from the chord length we can find the value of delta, and from the radius we can calculate the arc length. Then we can calculate the value of r sin phi. K value we can take it as 1 because it is not given. This is the radius of friction circle, which is equal to 1.74 meter. Then we have to calculate the value of A, which is equal to r into arc length by chord length. Then we have to do the graphical construction like this. First we have to draw the slope to some scale. Then here one end of the slip surface is known to us, that is nothing but to point. To find the other end of the arc, we have to use the chord length. So here in the problem chord length is given because center is not known. We should use the chord length only. So chord length is given as 27 meter. So by taking 27 meter from this 2 point, we can find the intersection point on the top of the embankment. That will become the other end of the arc. So knowing these 2 points, we can take the radius and we can find one intersection point, which is nothing but center of slip circle. So after locating the circle, then we can take the r value, and from the center we can draw the slip surface. Then we can also find the delta value. After that, we have to draw the friction circle with radius kr sin phi. Then we have to mark the total weight with respect to the toe point, because the distance is given with respect to toe point. By taking the distance, we can draw one vertical like this, representing the weight of the sliding soil mass. Then we have to draw a line parallel to chord by taking a distance A from point O. By measuring the distance point from the point O, so at a distance of A, we can draw the line parallel to chord. So that represents the total cohesive force. Then from this intersection point, we have to draw a tangent to the friction circle, which represents the resultant reaction. So all these lines we have to extend like this, and then we have to draw a line by taking the W value to some scale. By taking the W value to some scale, we will be getting the load scale. Then we have to draw a line parallel to this total cohesive force like this, so that this triangle is formed. From this force triangle, we can measure the distance, this PR, which represents the total cohesive force. Suppose it is some 1 centimeter, multiply with the load scale. So that we will be getting the total cohesive force. So after getting the total cohesive force, we should equate it to mobilized cohesion multiplied by chord length. Then we will be getting the mobilized cohesion, which is equal to total cohesive force, which is obtained from the graphical solution, divided by chord length. So after getting the mobilized cohesion, we can substitute in the equation of factor of safety with respect to cohesion, which is the ratio of ultimate cohesion divided by mobilized cohesion. Ultimate cohesion is already given in the problem, that divided by mobilized cohesion, whatever is obtained from the graphical construction, so that we can find the factor of safety with respect to cohesion. So here in this problem, figure is given, and from the figure we can find the values of delta, and here slope angle is also given, height of the slope is given. So here radius is given, height is given, and angle of inclination, this is 45 degrees. Phi value is given, C is given, gamma is given. So we should find the factor of safety with respect to cohesion using the friction circle method. Here total weight is given, and its distance is given with respect to point A, that is from the toe point. So here also we should do the same graphical construction. First we have to draw the slope to some scale, and then we have to locate the center of slip circle using the data given in the diagram, and then we have to draw the sliding soil mass. So after that we have to draw the friction circle, then total cohesive force, then we have to construct the force triangle. From the force triangle we can find the mobilized cohesion. Actually we will be finding the total cohesive force. See, from that we will be finding the mobilized cohesion. Then by taking the ratio of ultimate cohesion to the mobilized cohesion, we can estimate the factor of safety with respect to cohesion. Then the next method is Taylor stability number. So in this method, we can estimate the factor of safety with respect to cohesion using the non-dimensional number called as Taylor stability number, represented with symbol Sn, which is equal to mobilized cohesion divided by unit weight of soil into height of slope. So we know that factor of safety with respect to cohesion is the ratio of ultimate cohesion by mobilized cohesion. We can also write it as mobilized cohesion equal to ultimate cohesion divided by factor of safety. So from this we can also write this stability number as C by Fc into gamma into H. By substituting the value of Cm as C by Fc, we can write the stability number as C by Fc into gamma H. We also know that factor of safety with respect to cohesion equal to critical height divided by height provided. So by taking this critical height into the equation, we can write the stability number as C by gamma into Hc. We know that Hc equal to Fc into H. From this we can write Fc into H in place of Fc into H, we can take it as Hc. So C by gamma into Hc. So using this Taylor stability method, we can also estimate the critical height of a slope. So the advantages with this method are we can easily estimate the factor of safety with respect to cohesion without any graphical construction. We can also estimate the critical height of the slope, and we can also find the critical slope angle. So from this we can write, if you take the factor of safety equation, we can write it as C by Sn into gamma into H. Or we can also write it as stability number equal to C by gamma into Hc. Then if the slope is submerged, then in the equation we should take the submerged unit weight. Suppose if the slope is subjected to sudden drawdown condition, then we have to use the reduced angle of friction, which is equal to angle of internal friction multiplied by submerged unit weight divided by saturated unit weight. So corresponding to this 5D value, we have to find the stability number. See, in this method, stability number values are given with respect to different values of phi and even I values. Corresponding to different I and phi values, stability numbers are given in the form of tables and charts. So by finding the stability number value corresponding to the I and phi values, we can estimate the factor of safety. So here if it is subjected to sudden drawdown, we have to find the Sn value corresponding to 5D. Then if the slope is saturated, then we should take the saturated unit weight in the equation. Suppose if the slope is having one hard stratum which is located at a reasonable depth below the toe, then there is a possibility of compound failure. So in such cases, we have to take the factor which is called as depth factor into consideration. So this depth factor equal to depth of the hard stratum divided by height of the slope. So Taylor presented the values of stability number for different values of slope angle and df. So there is another table available to find the stability numbers for the given I value and df values. There is one example. An embankment has to be constructed with a soil whose C equal to 20 kPa, phi equal to 20 degrees, gamma equal to 18 kilonewton per meter cube, factor of safety equal to 2 and height of slope is 6 meter. Estimate the side slopes to be used given the stability numbers for different slope angles. Also calculate the factor of safety if the slope is 1 vertical to 2 horizontal. So here one table is also given for different values of I, stability numbers are given. So in this problem, first we have to write the equation for stability number, which is equal to C by Fc into gamma into H. So here it is asked to estimate the slope. First we have to estimate the side slopes to be used. So for the slope angle, initially the slope angle is to be estimated. So here C value is given, Fc value is given, which is 2, gamma value is given, and height of the slope is also given as 6 meter. By substituting all these values, we can calculate the stability number, which is coming as 0.0926. So corresponding to this value, we have to find the value of I. So by using interpolation method, we have to find the I value. So which is coming as 58.22 degrees. So that is the first part of the question. And here it is also asked to calculate the factor of safety if the slope is 1 vertical to 2 horizontal. So when the slope is 1 vertical to 2 horizontal, then I equal to 26.56 degrees. So by taking tan inverse 1 by 2, we will be getting the I value. So which is 26.56 degrees. Corresponding to this I value, we can find the stability number from the table, which is coming as 0.018. So corresponding to this value, we can estimate the factor of safety by taking the same equation once again and substituting the value of Sn. So Fc equal to C by Sn into gamma into H. So that we can estimate the factor of safety, which is coming as 10.21. Another example is an embankment is inclined at an angle 35 degrees and its height is 15 meter. So here I value is given, H value is given, the angle of shearing resistance phi value is given, cohesion is given, gamma is given, then Sn value is given. So we have to find the factor of safety with respect to cohesion. So we can use the same equation Sn equal to C by Fc into gamma H, in that all the values are given except this factor of safety which we have to find. Then another example is here determine the factor of safety with respect to cohesion and critical height of slope. Critical height of slope means HC. For a submerged embankment, here the slope is submerged. So we should take the submerged unit weight. And here stability numbers are given, soil properties are given, and we can use the same stability number equation. So here initially we have to find the factor of safety with respect to cohesion, where C value is given as 40 and Sn value which is obtained as 0.097 corresponding to I value of 40 degrees. Stability number is 0.097 from the table, and we should take the submerged unit weight. So here saturated unit weight is given, that minus unit weight of water. We can find the submerged unit weight multiplied by height of the slope is 10. So from this we can estimate the factor of safety with respect to cohesion. Then we should also find the critical height of slope, which is equal to Fc into H. So Fc value is obtained as 5.04 and H value is 10. So that we can find the critical height as 50.4 meter. Another example is a new canal is excavated to a depth of 5 meter below ground level through a soil having C equal to 15 kPa and phi equal to 15 degrees. Void ratio, specific gravity are given. Slope is given as 1:1. Calculate the factor of safety with respect to cohesion when the canal is running full and under sudden drawdown condition. So when the canal is running full, we should take the submerged unit weight, and when it is subjected to sudden drawdown, we should take the reduced angle of internal friction, which is equal to phi dash into gamma dash by gamma set. So here it is coming as 7.52. So corresponding to this phi d value, we should take the stability number. So these are the stability number values corresponding to different phi and I values. So in the initial part of the question, it is asked to estimate the factor of safety with respect to cohesion when the canal is running full. So when the canal is running full, we have taken the submerged unit weight and corresponding to this phi value. So phi value is 15 degrees and I value is 45 degrees because the slope is given as 1:1. I value is 45 degrees. So corresponding to these two values, the stability number is 0.07975 from the table. So from this factor of safety is estimated. Then in the second case, when the canal is under sudden drawdown, we have to find the submerged unit weight. So from the void ratio and specific gravity, we can estimate the submerged unit weight and saturated unit weights. Then we can substitute in this equation and then we can estimate the phi d value. So corresponding to this phi d value and this slope angle, we have to find the stability number from the chart. Then we can substitute in the equation of factor of safety and then we can estimate the factor of safety. So here 4 conditions are given. One is the immediate stability of slope after construction, long-term stability of slope, long-term stability of slope after full submergence, and stability on sudden drawdown. So here also table is given to find the stability numbers with respect to phi value. So in the first case, it is asked to estimate the immediate stability of slope after construction. So immediately after the construction means we should take the total shear parameters. So when you take the total shear parameters, phi value is 0. So corresponding to phi equal to 0, the stability number is 0.17. So this value has to be taken in the equation and we should take the value of unit weight, which is given as 18.13 in this equation, so that we will be getting the factor of safety. In the second case, long-term stability of slope is asked. So for the long-term case, we should take the effective shear parameters. So we should take C dash and phi dash. So here for the short-term or immediate stability, we should take the total shear parameters, whereas for long-term condition, we should take the effective shear parameters. So here total cohesion is taken, but here effective cohesion is taken. So effective cohesion divided by, we should take the stability number corresponding to effective angle of shearing resistance, that is 15 degrees. Then we will be getting the factor of safety. Then third point is long-term stability of slope after full submergence. When it is fully submerged, we should take the submerged unit weight. And when it is fully submerged, we should take the effective shear parameters. Okay, because it is asked long-term stability. Then fourth case is stability on sudden drawdown. So for sudden drawdown, we have to find the value of phi d, and then corresponding to this phi d, we should take the stability number. And in the equation, we should take the saturated unit weight. If it is subjected to sudden drawdown, we should take the stability number corresponding to phi d, but unit weight, we should take it as saturated unit weight. Next example is a temporary cutting 8 meter deep is to be made in a clay having a unit weight of 18 kN per meter cube and an average cohesion of 20 kN per meter square. A hard stratum of rock exists at a depth of 12 meter below the ground surface. Use Taylor stability curves. Estimate if a 30-degree slope is safe. If a factor of safety of 1.25 is considered necessary, find the safe slope angle. So here the slope angle is given and for the slope angle and depth factor. Depth factors, so three depth factors are taken. Here the stability numbers are given. So here first we have to find the depth factor. Here location of hot stratum is given as 12 meter below the ground surface. So 12 divided by H value. H value is 8 meter. So 12 divided by 8, it is coming as 1.5. Then depth factor is 1.5. So we have to take this column. Then I value is given as 30 degrees. So here slope angle is 30 degrees. So for 30 degrees and depth factor 1.5, the value is 0.164. So taking this stability number into the equation, we can estimate the factor of safety, which is coming as 0.85. And here the factor of safety of 1.25 is considered necessary. So because it is less than 1.25, it is unsafe. And in the second case, we have to take this factor of safety into consideration, and then we have to estimate the slope angle. For that, let us take the FC value as 1.5 in the stability number equation, and let us estimate the stability number first, so which is equal to C by FC into gamma into H. So stability number value is coming as 0.11. So corresponding to DF is 1.5, we have to find the I value corresponding to stability number 0.111. So which is coming as 10.48 degrees. From the interpolation method, it is coming in between these two. So we'll be getting the I value as 10.48 degrees. Then stability of infinite slope. So for evaluating the stability of infinite slope, we should know the equation for factor of safety. So if we take the slope, this one is infinite slope, and we know that for infinite slope the soil properties are same at identical depths. So here if we consider a slip surface which is located at a depth z below the surface of the slope with the slope angle I, then for the plane AB, the vertical stress on plane AB, which is taken as sigma z, equal to weight of prism ABCD divided by area of plane AB. So here weight of prism ABCD, we should take area of this, volume of this multiplied by unit weight of soil. So here we can take the volume as Z into this thickness is Z and width is B cos I, width is B cos I. So Z into B cos I. If you take the unit thickness, then multiplied with the unit weight of soil, you will be getting the weight of prism. That divided by area of plane AB. Area of plane AB is nothing but B into 1. By taking the unit thickness, the cross-sectional area is B into 1. So that we will be getting the value of vertical stress as gamma z into cos I. Then normal stress on slip surface, that is this one, which is perpendicular to the plane AB, equal to sigma z cos I. If the angle between this normal and vertical is I, then it will be sigma z cos I. So sigma z value already we have calculated as gamma z cos I into cos I. We will be getting gamma z cos square I. Then shear stress equal to sigma z sin I. We are just resolving the sigma z into horizontal and vertical components. So sigma z sin I, sigma z is gamma z cos I into sin I, gamma z cos I sin I. Then if the soil is portionless soil, if the infinite slope is made up of portionless soil, then the factor of safety will be factor of safety with respect to friction, which is equal to tan phi by tan I. So here if you take the shear strength of soil divided by shear stress, then you will be getting sigma value. Sigma value is nothing but gamma z cos square I into tan phi divided by 2 value shear stress. Shear stress is gamma z cos I sin I. So by taking this ratio, we will be getting tan phi by 10. So factor of safety of portionless soil is independent of depth z. In this equation, z is not there. So it is independent of depth z. And the slope will be stable up to I less than 5. So when the I value is less than 5, then only this factor of safety will be greater than 1. So it is stable up to I less than 5. Then in the second case, if the soil is coarser soil, that is C5 soil, then the factor of safety equal to, here C is not equal to 0, so C also will come into the equation, shear strength divided by shear stress. So here if we observe this equation, here factor of safety is depending on Z value. And for a given slope angle I less than 5, the slope will be stable up to a certain depth ZC called as the critical depth. So if you take the factor of safety as 1, then, and if you equate to this equation, we will be getting the critical depth ZC. So here instead of Z, if you take it as a ZC, we will be getting the ZC value as C by gamma into cos I sin A minus cos square A tan phi. So if you take out this equation on this side, then C by gamma into ZC equal to cos A sin A minus cos square A tan phi. So if we observe this part of the equation C by gamma ZC, it is something looking like C by gamma into HC. What is C by gamma into HC? It is nothing but stability number. So if stability number is not given, for infinite slopes, we can use this equation cos I sin A minus cos square A tan phi. Using this equation, we can estimate the stability number. Here one example is there. An infinite slope is made up of clay with the following properties. Gamma value, gamma dash, C dash, phi values are given. And the slope angle is given, height is given. Now we have to find the stability of the slope when the slope is submerged and when there is seepage parallel to the slope. So when the slope is submerged, then we should take submerged unit weight in both numerator as well as denominator. So here because it is infinite slope, we should take the infinite slope equation for factor of safety. And because it is C5 soil, we should take both the C and phi into the equation. And because it is submerged, we should take the submerged unit weight both in numerator and denominator so that we can estimate the factor of safety. But in the second case, there is seepage parallel to the slope. When there is seepage parallel to the slope, we should take submerged unit weight for the shear strength and saturated unit weight for the shear stress. So here in the numerator, we should take gamma dash, and in the denominator, we should take gamma set. And then we can estimate the factor of safety.